Welcome back to our Modbus primer. In this lesson, we'll shift our focus specifically to Modbus RTU and walk through some technical details behind how it works. Here's what we'll cover in this lesson: a quick intro to Modbus RTU and its role in industrial systems, the Modbus RTU message structure, breaking down the protocol data units and application data units, how Modbus RTU messages are framed at the byte level, the master-slave message flow between devices, how CRC is used for data integrity, and finally, critical timing considerations like silent intervals and intercharacter gaps. By the end, you'll have a strong technical understanding of Modbus RTU. Okay, before we get into it, let's briefly recap. Modbus RTU is a serial communication protocol that's popular in industrial automation because it's both efficient and reliable. It uses a master-slave model, typically over RS-232 or RS-485 lines. And why is it so widely used? It's efficient, using compact binary format that saves bandwidth. It's reliable, thanks to CRC error checking. And it's versatile, found in everything from factory control systems to energy meters. Now let's look at how messages are structured. Okay, so Modbus messages are made of two main parts: the PDU, or Protocol Data Unit, and the ADU, or Application Data Unit. So let's break these down. The PDU includes a function code, which defines the requested operation, and a data field, which contains the details needed, like register addresses or values. The ADU wraps the PDU with an address field to target a specific slave, and a CRC field to check for errors. So the PDU defines what to do, and the ADU makes it deliverable and verifiable. So now that we've covered the PDU and ADU, let's talk about how Modbus RTU messages are framed for transmission. This framing is essential for ensuring that each receiving device can correctly interpret each message. The application data unit forms the complete Modbus message sent over the network. It includes all the key components we discussed earlier: address, function code, data, and CRC. To transmit this message physically, each byte of the ADU must be properly framed. This is where byte-level transmission comes in. In Modbus RTU, each of these framed bytes is referred to as a character. And for each character, we begin with the start bit, which marks the beginning of the byte. Then we have the data bits, which hold the actual content, such as an address or part of the data field. An optional parity bit can be included for simple error detection. And finally, we have stop bits, 1 or 2, to signal the end of the byte. These framing components help ensure that each byte is recognized and processed correctly by the receiver. They're set up in our UART configuration, which handles the physical level transmission for Modbus RTU. So in summary, the ADU is a full logical message, and each byte of the ADU is framed with the start, data, and optional parity and stop bits, ensuring smooth and reliable communication from the physical layer up. Okay, now let's look at how communication flows in Modbus RTU. The master always initiates, sending a message in the form of an ADU. The slave receives the request and processes it. If it's valid, it sends back a response. If there's a problem, it sends an error response. This is a strict master-driven model where the slave only replies when spoken to. And with regard to data integrity, Modbus RTU uses CRC, or cyclic redundancy check, which helps verify that the data has been transmitted without errors. Modbus RTU uses CRC16, which generates a 2-byte checksum from the message data and appends this CRC at the end of the frame. On the sender side, the CRC is calculated and appended. On the receiver side, CRC is recalculated and compared. If it matches, the data is accepted. If it doesn't, the frame is discarded, and the master may retry. This simple check helps detect and reject corrupted data, making communication much more robust. Now let's cover timing, which is just as important as the data itself. First, there's a silent interval. Before a message can begin, the bus must be silent for at least 3.5 character times. Then, during a message, there's an intercharacter gap. No more than 1.5 character times can elapse between bytes. If the gap is too long, the receiver assumes the frame is broken and discards it. So what's a character time? It's the time it takes to transmit one byte, including start, data, parity, and stop bits, and depends on the baud rate. In our project, we'll use UART idle line detection to detect when a frame has ended. For simple systems, this is enough, but for industrial-grade systems, dedicated timers are often used for tighter timing control. Alright, now that we've covered how Modbus RTU works under the hood, we're ready to move on to the next step, Modbus RTU addressing. We'll look at how devices are addressed and how that fits into Modbus function codes and data communication. Okay, so see you in the next lesson.